Okay, so let's get this started. I'm Matteo Carlini, I'm Software Technology Manager at Arm, responsible for the roadmaps of open source firmware, so Arm trusted firmware for A-class, and UEFI and platform software for the A-class platform as well. So today I'm going to present a talk that's about securing Arm servers, so that's basically mean exporting and executing secure services that are requested by the normal world as a management services, services that are usually relevant in the server and infrastructure space. So a little agenda, we will start from where we left back in San Francisco, because ideally this is a continuation of the talk that I did in San Francisco about secure boot. But still it's an independent talk if you didn't attend the previous one. And then I will go through the concepts of secure partitions, describing the architecture, and digging into the details that we changed in the firmware. And when I mean trusted firmware, I really mean trusted firmware A, so this has nothing to do with trusted firmware M at the moment. Changes into the EDK2 code base as well. And then I will introduce the support for the ARM system guidance platforms and all the work that we did for enabling these concepts on these platforms, so on the HKG18-104, that are real platform, modeling platform in which you can experience all the software stack that we are discussing. So let's start where we left in San Francisco. So back at the time, we were eating crabs at the Fisherman Wharves, for sure. But I did a talk describing secure boot, so the differences between trusted boot and UEFI secure boot, and how this maps with a complete chain of trust on the device. And finally, I landed to this slide that was basically giving a view on the framework on how to access from a secure world some variables, well, in general, whatever storage medium you would like to access from the secure world. So I will start describing this framework a bit better and pointing to the relevant work that we are doing both in the open source firmware and in the specification world at Arm. So let's start introducing the concept of secure partition. So what is a secure partition? So in Arm's wording, a secure partition is a software sandbox environment that runs in the secure world under the control of the trusted firmware, so under the control of the most privileged firmware. And you can use secure partition to run standalone management mode services as they are defined by the PI spec, so part of the UEFI umbrella specification set, the platform initialization spec. So which are the use cases that we have in mind that we would like to cover with this framework? So are listed there. So mainly two main areas that we would like to cover. One is, okay, I have a storage medium on my platform and I would like to access the storage medium from the secure world. The storage medium can be used for hosting secure variables, so keys, signatures, or whatever, but it may also be used for storing a firmware if you would like to do a secure firmware update properly. Another kind of services that we are looking into are the management services. So if you would like to have RAS error handling in the secure world, you can use this framework, as well as for BNC communication or errata handling. And then a question mark, whatever else services you would like to see ported on this framework, just let's have a talk, because we are interested in whatever use you can see on this framework for your platform and your SoCs. So this is a big picture on the software architecture from a functional block point of view, which are the assumptions that we did from a software design. So the secure partition is, as I said, an isolated sandbox environment. So each secure partition is isolated and it has limited access to system resources. So it does not have a full view of the system, even though it instantiates and it works in the secure world. It is OS agnostic, and it obviously leverages the ARM specification, so the MM interface at the moment, Trust Zone, and also the UEFI standalone MM as defined in the PI spec, as I said. A point that I would like to highlight is the possibility to use the same code that you usually run in the normal world. For example, from EDK2, you have a module that runs in the normal world. You may reuse it in the secure world into a secure partition, and you may run it as a standalone NMAN driver. So this is quite important from our perspective because it allows you to reuse the code that you already have in the normal world. You can port it and reuse in the secure world. And well, last point, quite important also. So it reduces the need for stuffing and plugging specific management service code into EL3 and into the runtime firmware. That's not what we would like to see in the future. So which are the changes, the main changes in the trusted firmware? So SPM is the acronym for Secure Partition Manager. So this is the functional block that is responsible for a lot of things, so that are listed there. So basically it instantiates the secure partitions, and it prepares the environment in the secure world for the secure partition to run. The SPM will implement all the interfaces that are standard today and in the future, so that will be standardized as time goes by our architecture guys. Interfaces for all the three use cases listed there. So for the SPM itself to instantiate the secure partition, interfaces for the secure partition to fulfill the services, and interfaces from the for the non-secure world, so for the normal world, to request those services in the secure world. If you work with trusted firmware A, you may be familiar with the SPD, so the Secure Payload Dispatcher. SPD and SPM are not the same thing, and most important, they are mutually exclusive. So if you're working currently with an SPD, and if you try to compile the SPM, you have to turn the SPD off. In the future, we see the SPM will basically track the evolution of the spec, and the two are substantially different because the SPD does not enter into the management of the trusted applications, but it delegates everything to the trusted OS, while the SPM takes directly care of the life cycle of the secure partition. At the moment, it takes care of it into EL3, but eventually, as we will see in some follow-up diagrams, it may end up into the secure EL2 as the architecture extensions will be available for it. So this is a slightly unrelated slide. So in the sense that it's not specifically related to the secure variable access problem that we are trying to solve. But this lists anyway other main changes that we did in the past 6 to 12 months into the trusted firmware A, specifically for RAS error handling. So these are the SDI dispatcher and the exception handling framework. So the exception handling framework is a brand new framework for handling RAS errors and for delegating them to lower exception levels. It currently supports the 8.2 RAS extensions, but we also have plans to support in the 8.4 extension as they become available. And it can be used by the delegation mechanism that's listed just below, so the SDI dispatcher. And the SDI dispatcher implements a piece of the SDI specification from ARM that's exactly the physical SDI dispatcher. So it allows normal world SDI client to register handlers in the secure world for receiving events that are coming, system events that are coming from the secure world. So I'm not describing here in this talk specifically a RAS framework. There are other talks that go through it. I just wanted to say that we have a working example of a RAS error handling using a DMC 620 memory controller on our ARM SGI 575. And I will present this platform just in a couple of minutes. But if you are interested, you can also have a look at the RAS example. So final thing to say on the trusted firmware is that everything that you see here is already upstream, is already in the GitHub project, and it will be part of the official 1.5 release that we will do right now this week. It's a matter of days because everything is ready. We are just under the final verification process. But the 1.5 tag will be out this week. All the components are already upstream, so you can just go and have a look at the SPM, SDI, and exception handling framework. So back to the concept of standalone MM and how to implement a secure service. Changes in the EDK2 code base, and all the credits for those changes goes to other Arm people, Achin and Sokowitz, that should be here in the room. So the standalone MM package is a brand new package that leverages that work done previously from Intel on the x86 on the SMM package. So this extended package and implements support for the AArch64 MM. And this is going upstream now in the EDK2 master branch. It has been previously developed under the EDK2, oh, I missed a 2, okay, EDK2 staging for a while, and now it's going to be upstream in the master branch, so you may want to have a look at it. And just below, the change that add the support into EDK2 of the FI-MM communication protocol that basically it's used for leveraging the MM spec, so calling the MM communicate SMC that allows the EDK2 firmware to perform invocations into the trusted firmware below. So these two set of changes, trusted firmware and EDK2, completes the set of changes that are requested to run an example of a secure services running into a secure partition. And we will see in 1 minute how this is implemented on one of these platforms. Now, I would like to spend a couple of minutes describing the Arm System Guidance platforms. They are out for free since a couple of years now. So you can go to the developer.arm.com and download this platform. So these are complete reference system designs for demonstrating the latest Arm IPs. So there are platforms for mobile, there are platforms for servers, and recently also for IoT, if I'm not wrong. We release the FVPs for them, and we had a discussion this morning about the availability and the license of this platform. So at the moment, you may download it for free, and then you have to get a license from Arm, and you have to basically accept an end-user license agreement. But as soon as you get it, you have a complete modeling example for the latest Arm IPs, not only for cores, but also for interconnects, interrupt controllers, memory controllers, a complete system. And we are maintaining within Arm a complete software stack, and we are now starting to upstream support for these platforms one by one. So we started with the HKG18-104 that I will describe in 30 seconds. It's the next slide. Other platforms are coming out soon. So this includes support into the Arm trusted firmware that has been recently pushed out, and for EDK2 platforms that's coming. As I said, other SGI are already planned. So 572, that's the previous one, and also for the mobile, the SGM775 for mobile. So now let's have a look finally at the 575 one. So the SGI575 is a 2018 infrastructure platform. So it's meant for modeling a server or networking or a storage platform. It features 8 ARM A75 cores on 2 clusters. It supports DSU with shared L3 cache. It has all the latest ARM IPs, so all the latest GIGSYS 600 interrupt controller, the latest MMU, and 2 DMC controllers for handling and also injecting RAS errors. Okay, it's not only a good modeling platform, it has some limitations. So which are the drawbacks? Well, the drawbacks are mostly the fact that being a model you don't have any kind of hardware support for storage medium, so you don't have an hardware secure storage on board. And we just rely on a simple flash partition for providing our example. You don't have any hardware support for crypto operations, so we just rely on software crypto leads for doing all the crypto operations. And obviously you don't have CD-ROM on it. So if you want to install a distro, and you can install a distro on top of them, you must select an alternate mount point, and the distro should allow you to do that. So the snapshot that I took from my laptop, you can see a BusyBox running on it. You can see the 2 clusters, each one with 4 A75 cores, and that's it. The next slide shows a Fedora distro running on top of the SGI. So we have the grab menu selection, Fedora 27, and we have the completed boot of Fedora. Not sure if you're able to read it, but that's Fedora 27. And we are currently able to run Fedora and Debian 9.3, and we are also able to run KVM hypervisor, so you can run multiple guest operating system on top of an 8.2 core. Let me reiterate that. So that's the only ready-to-go option for developing software on ARM 8.2 cores. Okay, so let's arrive to the example of the secure variable access on this platform. So how are we building this example that will eventually go upstream? So I tried to represent here the 2 stages, so the boot phase and the runtime phase of EDK2. The 2 stages had in common some modules, a crypto module and a variable SMM runtime module in the normal world. And in the secure world, what we ported, so we have a variable SMM module that will be copied into the standalone, into the brand new standalone MM package that we are just upstreaming. We have an OR flash driver that will be used for the real communication with the flash partition on the SGI 575. And we will also have, that's not yet there, but we plan to have a crypto lead that will be used for performing authenticated read and writes. So which are the steps that we are implementing using this framework? Well, 2 basic steps. One is the get variable part. So in the boot phase, the EDK2 boot code needs to verify the signature of the operating system before launching it in execution. And in order to do that, it needs to read the signature from the signature database that's stored somewhere in your storage medium. So it invokes a get variable API that goes through the MM communicate, arrives in the trusted firmware, it gets routed by the partition manager, and the partition manager will instantiate the secure partition. Then the call will arrive to the variable SMM in the secure world that will call the proper APIs of the NOR flash driver to perform the real read operation from flash. In this case, it's just a read, because the boot phase just needs to read the signatures. It doesn't really matter about writing variables. But the writing part is important and comes in usually at runtime when either the OS or even the EDK2, if you want, would like to call some runtime variables, so some runtime APIs, so set or get variable API. So the invocation will go through the very same exact path as the get variable before. So it will go through the MM communicate, down into the secure partition manager, into the runtime firmware, and then up to the variable SMM. In this case, the APIs will be authenticated, especially for write operations. So that's why we need a copy of the crypto leads in the secure world, because we want to protect the write operations into the storage medium. And this will be done in the secure world by that code. So at that point, again, the variable SMM module will interact with the NOR flash driver in order to access our poor flash partition in the 575s, because we don't have a proper secure storage medium. So that's the way we see happening the read and write case from the normal world, invoking a secure service into the secure world, running into a secure partition as a standalone ML. Last couple of slides on the evolution of this framework. So evolution number one, with the current architecture, the possibility to run multiple partitions at the same time, concurrently. Because at the moment what we have in place is just one single partition at a time. So this is the next step. And this step needs some little bit of support from spec perspective that our colleagues from Arm are kindly providing. So the MM interface will evolve into a secure partition client interface that will define how the normal world will interact with the secure world. And at the same time, in the secure world, the secure partition runtime interface will specify how the different multiple secure partitions will interact and talk with the secure partition manager. Being each secure partition isolated from each other, as I said initially. And just to reiterate, this will be again possible on the current 8.2 architecture. So we will provide in the future an example of, so we will extend the example that we have on the 5.7.5, embracing also these multiple partitions. And we will try to upstream everything again. So we will probably have a RAS example running together a storage access example. Second evolution, number two, that's way more in the future because these will require architectural support at CQRL2 in order to have possibly a piece of ARM trusted firmware running in the CQRL2. At that point, you will have the possibility to run secure partitions in CQRL1, so multiple partitions that will embrace CQRL1. At only at this point, you may run a trusted OS with its own TLs as usual. So this will be the common trusted OS, OPT or whatever. And you may run in parallel some secure services like MM services that can run either at CQRL1 or at CQRL0 as before. So this is the final scenario, and this also opens some possible commonalities with the mobile world, because you may also want to have a trusted OS with multiple services in the mobile world. Why not? Or multiple trusted OSs, Charles kindly suggests me. So this is it, really. I have 2 minutes left, and no more slides. So just questions.
I have a question. You talked about SGI 575 and SGI 520. What's the difference between those two?
SGI 575 is the latest one that includes support for 8.2 cores, so for the A75 core. Then these one are the previous one. So the 572 was the so-called Ashbrook. It was based on the A72. And these were mobile platforms. This is the 8.2 based mobile one.
Okay.
So if you would...
Those are still FVP, right? So it's FVP implementation
Correct.
A72.
Correct.
Okay.
Yeah.
Okay.
So if you would like to see more support coming upstream for other system guidance platforms that you are using, just come ask us and we may have a chat. Other questions? If not, the last slide provides all the pointers to everything that I said. Specs, pointers to the trusted firmware documentation upstream for the secure partition manager and the SDI dispatcher. Pointers to the FVP and to the system guidance, and pointers to the platform support just upstream. EDK2 is coming soon, but very, very soon.
Can you ask for these slides there?
Sorry?
So we're just developing the PCI and SPRT that got mentioned. So we're just doing the SPCI and SPRT specifications that got mentioned earlier, and we can stick links in there So if anybody wants to help us with those specs or review them, we can put links in there before that gets shipped.
Yeah, yeah.
Because they went out to the drop zones literally
Friday last.
Friday. Yeah, just before
So
the conference.
what's the major difference between SPCI and current MN definition in the PI spec?
That's your question.
The main difference is the SPCI spec enables asynchronous message passing between the normal world and secure world. So the communicate is a synchronous interface. So you go into the secure world, do your work and come back, and the normal world keeps waiting.
Right.
But the SPCI kind of breaks down the communication. So you post a request, get a token, and at a later point of time you query. Either you can query for completion, you can query whether the request completed, or you can get a notification in the secure world saying that the request done. Yeah, so that's one. The other thing is, like in terms of, if you think about a world with virtualization on both ends, right, then there are issues around how memory gets shared, because it's now passing through not just one translation regime, but like say you will have guest physical addresses within a normal world VM, and the same thing can happen on the secure world side. So it specifies interfaces which enable